All right, good morning. Welcome to the session with PowerShell Engine Internals. My name is Dongbo. I'm from the PowerShell team of dev in the PowerShell team. This talk is about the design and implementation of the PowerShell engine, of some key components of the PowerShell engine. We'll look at the overall architecture from an end-to-end point of view, and we will walk through the execution of a simple script and deep dive into some of the involved components. So this diagram is basically what happens when you are running a script from PowerShell console. So here, the script I'm using is quite trivial. It's assigning a string to $pass and then run their $pass. So when you press enter in PowerShell console, this is what happens in the console host. First, the console host will read input from the console. Then you're going to create a pipeline object with two commands. The first one is whatever string, whatever script I typed into console. The second one is out default. This out default is a special command in PowerShell for rendering the results and arrows produced from the user script onto the console based on some predefined formatting. So it works closely with the formatting system in PowerShell. Whenever we run anything from the PowerShell console, out default will be appended to the end of the pipeline. And it takes the pipeline input, and whatever result get into the pipeline will be captured by out default, and the object will be rendered onto the console based on some predefined formatting. Okay, back to the console host. Finally, the console host will call pipeline.invoke to start a new thread. We call that new thread the pipeline execution thread. And what it does is it's going to result, like if you look at these two commands, they are strings, they are text commands. So what the pipeline execution thread does is that it's going to resolve those text commands into command processors and then create a pipeline processor to run them all. So here comes the question. What is a command processor and what is a pipeline processor? Simply put, a command processor is where commands execute in PowerShell. There are three command processors defined in PowerShell. The first one, the type name is command processor. Well, the name is a little too general, but in fact, it only handles the C# commands and advanced functions. So advanced functions, they are essentially just functions and scripts declared with parameter binding attributes or parameter attributes, command binding attributes or parameter attributes. This set of commands, including the command and advanced functions, they have the common parameter support from the runtime, which means they, you can use dash verbals, dash arrow action, dash warning actions, and etc. parameters on those commands. And it also has full access to the parameter binding features. That means you can use dynamic parameters, you can use parameter sets, you can use pipeline parameters for them. So here comes the question. Well, I'm sorry. So one of them is, if we look at this two, oh, what's happening? Oh, sorry. So these two kinds of commands, one is command implemented in C# code, living in assembly. The other one is script. So how come these two are put in the same bucket? It turns out internally advanced functions are represented by a special internal command type named PS script command. As you can see from the screenshot, it's an internal type, and it derives from the PS commands, just like any regular C# commands. And this is why we also call advanced functions a script commands, because internally it is a command. It's backed by a real C# type. So second one is a script command processor. It handles the simple script, which are essentially the functions and scripts defined without the command binding parameters, the command binding attributes or the parameter attributes. This set of commands, they don't have the common parameter support from the runtime and restricted parameter binding rules are applied to them. For example, you cannot use dynamic parameters with those simple functions. The last one, native command processor. This one is straightforward. It handles the native executables, like ping, git, ifconfig. So in order to run a command, four key methods are implemented by every command processor. They are do prepare, do begin, do execute, and do complete. The do prepare, it's called once. It's called only once on the command processor before do begin. It's used for set up the context information and do parameter bindings. So for the native command processor, it do something more, like it's gonna start the executable process and redirect the standard input, output, and error streams as needed. The do begin, it's called only once before do execute. So for the command processor, do begin will actually run the begin processing method on the underlying commandlet. For the script command processor, do begin will run the begin block of the underlying script. For the native command processor, it's already been set up in the do prepare phase, so it does nothing in the do begin. Do execute. Well, do execute runs 0 or multiple times, depending on its position in the pipeline or whether or not there's any pipeline input. So say if you have a command, it's the first command in the pipeline, then this do execute will be called exactly once. But if your command is in the middle of a pipeline, then it's totally driven by the pipeline input, which means if there's no output from any upstream command, there's nothing written into the pipeline, then nothing will drive the do execute to run on this command. So for the command processor, do execute will bind the pipeline parameters, like anything written into the pipe, then the do execute will read that input and bind that input to the pipeline parameter defined for the commandlet. And then it's gonna run the process record on the commandlet. For the script command processor, it will bind the pipeline input to $_ and then run the process block on the underlying script. For native command processor, it will basically just feed the pipeline input to the executable process by, write that into the redirected standard input. And do complete, it's called only once after do execute. It's for wrapping up the execution of a command. For the command processor, the do complete will actually run the end processing message on the underlying commandlet. For the script command processor, do complete will run the end block on the underlying script. For native command processor, it's gonna wait for the executable process to exit and do some folder cleanup. All right, so now we have a basic idea about what are the command processors and what they do. So the next thing we want to look at is how do we resolve a text command into a command processor. So we go back to the pipeline, go back to the console host. As we talked before, the pipeline object here contains 2 commands, but both of them are in the form of text. So they are strings. You cannot just run stuff with string. You have to resolve the string into the actual command. So from the pipeline execution thread, the 2 text commands need to be resolved into the corresponding command processor. For the first one, it's trivial. It's just a script. It's a string of a script. So you're going to need a scripting command processor. So what happens is that the parser will kick in to parse this text into an AST, which is an abstract syntax tree. And then the AST is going to be used to create a script block. And then a script command processor will be constructed with the script block. So it's like the script command processor is holding a script block in it, and script block is holding an AST in it. It's something like that, simply. And for the next one, for the second one, our default is a command name. Things are relatively complex to resolve a command name. The command discovery component will kick in for the resolution. Okay. So command discovery. The command discovery component is where PowerShell looking for a command based on a given command name. The algorithm of the search is roughly like this. There are 3 events involved in this search. the pre-lookup event, the post-lookup event, and the command of found event. So first, the pre-lookup event will be triggered if it's registered. And as a user, you can define such an event handler, and you can assign, you can decide which command to return as a result by setting this command property of the event argument. And then you can tell the search to stop. If the search continues, then it comes to the second step, where PowerShell will look for the command through the scope chain. You're going to start from the immediate scope, and then go up, and so on. Go up to the parent scope, and so on, until reaching the global scope. It will try to find the command based on the given name in the order of alias, function, commandlet, PS1 file, and application. So one thing worth to be mentioned is that, like in PowerShell, many of the stuff are actually kept in the scopes. For example, functions, variables, commandlets, and alias, they are actually saved in the scopes. So what PowerShell does here is just going up the scope chain, trying to look for the command based on a given name. If it finds it, great. The command is found. It just return back the result. If it doesn't find it, then the module discovery will be triggered. The module discovery is it's for searching for the commands from the modules available in the module path. So it's the module autoloading. I guess we're all familiar with. What happens in it is that the module analysis will kick in to analyze all the modules available in the module passes to get back a table of commands exported from all the available modules. There are two kinds of analysis available in PowerShell. One is the lightweight analysis, and one is the heavyweight analysis. So by default, PowerShell will use a lightweight analysis, which is basically reading the metadata from the module manifest to look for all the exported members from the module. Or if it's a script module, say a PSM1 file, you're going to parse it to get an AST and analyze the AST to find all the exported members. If it's really had to, then PowerShell will fall back to the heavyweight analysis in this step, which is calling this import module that's list available. What does this command does is actually going through all the process of loading a module without actually loading its elements. So it's more expensive. Usually, it will be sufficient enough. Usually, the lightweight analysis is sufficient for most of the scenarios. So after the module analysis, we'll get back a table of commands, of the exported commands from the modules. And that result will be cached into the current PowerShell process. So it can be reused by by another command discovery, a search request happens in the future. Not just like that. Furthermore, PowerShell tries to serialize this result cache into a file on the disk so that another PowerShell process can also benefit from it. And this serialization, deserialization, it's made to be as simple and efficient as possible. A serialization request will be triggered when there's any update to the cache. But the write operation to the file is actually held until the cache becomes relatively stable, which means until there is not too many changes on the cache. So that we know that, okay, we write this cache into file once and it can be reused again. You don't have to write it again after the cache to be changed. So the serialization to file happens via a task in the background thread. So it's in a totally asynchronous way. And instead of depending on the mutex to guard the read-write operation on the file, PowerShell simply depends on this file lock, which means, okay, if I'm able to open a file, which means the file is not used by any other process right now, great. I'm going to read the result cache result from this file and just benefit from it. Or I'm going to write my updated cache into the file so that the other process can benefit from it. If I'm not able to open the file, which means the file is being used by another PowerShell process, then for the read operation, PowerShell will wait for, we'll try 2 more times with a 25-millisecond interval. The reason is that we really want to skip the module analysis step if it's possible. However, PowerShell will give up after 2 more tries and turn back to the module analysis. If it's a write operation and I cannot open a file, then PowerShell will just skip this write operation because a serialization request will always be triggered by the next update to the cache. So it will happen later. We can wait on that. After this whole module discovery process, we'll get back a table of command that's exported from all the available modules. And then we're going to use that table. We're going to try to find a match of the given, based on the given name, given command name in the table. If a match is found, awesome, then we can just load that module and return result. If a match is not found, sorry, can't do anything more. Like, we just have to give up. So if we were successfully get back a result, the command result, then this post lookup event will be triggered if it's registered. The found result will be passed into the handler, and as a user, you can decide whether you want to return that command or not by setting the command property of this argument of this event argument. And if the command is not found, then this command not found event will be triggered. And similarly, you can decide which command you want to return by setting this property. Okay, now let's see we successfully get back the result of this command. And the result get back will be a command info object. And based on the command type of this command info object, the corresponding command processor will be created with this command info object and return back. And this is how we resolve a command. So back in our diagram here, so after the command discovery step, this command processor out default is resolved. Like the string out default is actually resolved into the command out default, and command processor instance will be created with the command info object. And now we have both commands resolved, and PowerShell will create a pipeline processor, and to chain them together with pipes and start to execute. So chain them together with pipes. Here comes another question. Pipe. What is a pipe? A pipe is pipes are where command processor are going to write the out streams to. The out streams including the output streams, like anything you write out using write output, or arrow streams, anything you write out using write arrow, or warning strings, or debug strings, like stuff like that. So all those strings will be written into pipes. And whenever you add a new command processor into a pipeline processor, this command processor will be set as a downstream command of the previous command processor's output pipe. So in our example here, our default is added to the end of the pipeline, and thus our default will be set as a downstream command of the output pipe of this script command processor.
So did I understand you right? Downstream commands could actually operate on the output of like the debug and warning streams?
It can work on, well, regularly it can only work on output streams. Okay. But still, other streams are also written into pipe. It's just that when you are writing that stream into the pipe, in a different pipe, that pipe will not do anything on the downstream command. Only the output pipe, it will do something on the downstream commands. And we will look at that. So let's see, in our example, our script is going to run and produce some result. And the result object will be written into the output pipe. It's going to be add to it by calling this add to pipe. And this is the implementation for the add to pipe. What it does is that it's going to trigger the do execute message on the downstream command. So whenever you write something into the pipeline, actually into the pipes, the add to pipe method will be invoked, and inside it, the do execute method on the downstream command processor will be invoked. So this is how 2 or multiple commands in PowerShell are chained together in the pipeline. And this is how the output of one command flows to the next and triggers its execution. This is also why, like I mentioned earlier, that the do execute message on command processor. Like if the command is in the middle of the pipeline, like it's not the first command in the pipeline, then it's totally driven by the pipeline input. Because if there's nothing written to the output pipe of the previous like upstream command, then this do execute method on the downstream command will never be called. All right, then let's back up a little bit and go back to see how the pipeline processor is actually runs. The pipeline processor will basically call into this 4-key method implemented by every command processor. I will call, first we'll call do prepare on every command processor within the pipeline processor. So allow them to, give a second, sorry. Allow each of the command processor to set up the context information and do parameter bindings. Then it will call do begin on every command processor to allow them to initialize themselves. And then it will call do execute on the first command processor, only on the first command processor. So if there are any output produced from do execute on the first command processor, great. The output will be added to the pipe of the first command processor, which will trigger the do execute of the second command, and so on and so forth. It's like, and after that, okay, one thing to be noticed that the output can also be produced from the do begin, because remember, do begin will call into begin processing method of a command or the begin block of a script. So output can be produced from the do begin. When output is produced from do begin, it's the same. The output is written into the out pipe of the current command processor, which will trigger the do execute of the next command. However, by that time, the do begin of the next command hasn't been run yet, which means the second command hasn't been initialized. That will cause problem. And the solution to that is that, okay, within the do execute, you're going to call do begin for the first thing, if do begin has never been called already. And do complete will be called on every command processor after all the do execute finished, to allow every command processor to wrap up. And similarly, output can be produced from do complete, because do complete will call in processing on the underlying command or the in block of the underlying script. So again, the output from do complete will trigger do execute on the next command, and so on and so forth. But by that time, the do begin has already been called, so it's OK. All right, then we go back to this diagram. And we know that, OK, for this simple script over here, it only has an in block, because we don't define the begin and process block of it. So by default, it only has an in block, which means this script block here will run when this script command processor, when the do complete is called on the script command processor. All right, so do complete is called on the script command processor, and the execution starts. Now let's look at how this script actually runs behind the scene. So it's a script block. Remember, this script command processor holds a script block. The script block holds an ASD tree. So the compiler will kick in. Given the ASD tree, the compiler will visit every node of this abstract syntax tree and generate expression, real code represented by expression, generate the real code for every node of the ASD tree. And the result will be an expression tree. Expression is a linked expression in .NET. So it's something like, it's a concept of a code as data. So it's representing the code, but it's not some executable code yet. It's still a data, but it's representing the code to run. So PowerShell, the compiler, PowerShell compiler, take advantage of the linked expression. It goes through the ASD tree, visits every node, generates the expression tree representing the real action you're going to take on this script. So for our simple script, the expression block that's going to be generated will be something like this. Well, it's just roughly like this. The first thing you're going to do is that you're going to call a method. It's an expression call on a method, and to set the constant string value to this variable path, which is $pass here. And then it will start another pipeline processor to run the third pass. Okay, now, PowerShell compiler use the DLR. Well, DLR is .NET Dynamic Language Runtime. It's .NET framework. It's a framework built in .NET to support, using .NET to implement dynamic languages. So its name is Dynamic Language Runtime. PowerShell compiler uses Dynamic Language Runtime heavily in its code. It basically depends on dynamic expressions and call site binders to handle almost every one of the dynamic binding operations in PowerShell, including member access, method invocation, like indexing operation, or binary operations in PowerShell. Like all those dynamic binding operations are taken care of by dynamic expression plus a call site binder. Every call site binder, as you can see from the name, call site binder, a call site is like a place where an operation happens. For example, for method invocation, the place where you invoke this method is called a call site. A call site binder is a binder to handle this call site, which means to handle this dynamic operation. So for any call site binder, it has a fallback method, which is going to be responsible to resolve the dynamic binding and generate a real code, which is also an expression, and return an expression to this to return an expression for the DLR to execute. So one example, let's take this PS-get member binder as an instance. The PS-get member binder has a fallback. It has a method named fallback get member, and it's responsible for resolve the member access operation. So whenever you have any member access, say $file.name, then it's up to this binder to resolve that into the actual code. Like, what do you mean by $file.name? What's the value of a $file? And given me the $name, like the member name, how do I generate the code to actually access this property or field or whatever? So let's look at this $file.name closely. The compiler will generate such a code like this for it. It will first, call this method to get back the value of the $file, and then it will get an instance. It will get a singular instance of the PS-get member binder based on the member name. Like in our case, it's going to be the member name, and whether or not this member access is a static member access. And once you get back the binder, it will return a dynamic expression with this binder and this target, which is the value of the $file. So what happens internally? When this dynamic expression gets to run, it will ask the binder, hey, buddy, what am I supposed to do with it? Like, I don't know what to do with it. You're the binder. You tell me what to do with it. So the binder will call the fallback get member, and we'll do this calculating. We'll run some code to resolve this this member access operation, and generate an expression and return that back, and then tells the dynamic expression that, okay, here's the code, just run it. I have take care of the binding, return the code, just run the code. So a simple example here, what does this fallback get member does is that, okay, given this target, which is going to be the value for $file in this case, it's going to return an expression property, so which is a property access on the target with the property name. It's a simple example here. All right, that's binder. Well, as you can see, the binder, the call site binder, it's a really good concept that offers us a very clean way to organize the dynamic binding code. All the dynamic binding code lives in this fallback method. It's very clean. You know where to find it. And also, furthermore, it makes the script run much, much faster, thanks to its binding result caching behavior. So what happens actually, for the fallback method, it returns an expression representing the code to run. At the same time, it returns a restriction. The restriction defines under what condition you can actually use this expression to do this late binding operation. The restriction usually is based on the types of the passing argument. So For example, in our case, later we have another member access operation, which is $file2.name. And let's assume that $file and $file2 are of the same type. They're both, say, file info object. Then in that case, when again the dynamic expression gonna ask the binder, okay, what's to do? And the binder, this time will not call this a fallback in member method again because it don't need to resolve it. It's already in the cache. You can just return from the cache and be used immediately. So that we avoid this duplicate dynamic binding resolution, which is going to make the script run much, much faster. All right, now we have this expression tree generated from the AST. Great, we have the code. But expression tree is data. It's not real code yet. It's representing the code, but still it's data. It's data as code. So what to do with it? How do we run it? The answer is that we need to generate, turn this expression into a delegate. Let's see what we have on hand right now. We have an expression tree, which represents the actions to perform. And we have this runtime information, right? We have this run space, we have execution context, we have providers, whatever. These are the runtime information, runtime environment. So we have this actions to perform, and then we have this runtime environment where the action should be performed on. And naturally, we combine them together, we get a lambda expression representing a delegate that takes a runtime information object and do some actions on it. Great. Now we are one step closer. We got a lambda expression representing a delegate. But again, lambda expression is still an expression. It's still code as data. It's code. It's not real data yet. So next, Next, we need to actually generate a delegate from the lambda expression with the real executable code. And there are two ways to do that. The first one is that, okay, we already got the lambda expression. We can just call compile on it, which .NET can take care of to generate the IL delegate for this lambda expression. The IL delegate is a .NET intermediate language. It's the stuff that's in your assemblies on the disk. So for people who don't know about this IL, we're not familiar with it. It's like when you write any C# application, you compile it, it generates a DLL. The DLL contains the IL code. It's an intermediate language code. And later, the .NET Jetter, the just-in-time compiler, will take this IL code, generate the real native code to run on your machine. So that's IL. So the first option is that we call this compile message on this lambda expression to generate an IL delegate from .NET. And then the IL will be processed by the Jetter to generate a native language. And it's really fast. It's very efficient code. However, the drawback on that thing, on this approach is that compiling the lambda expression into IL delegate is very expensive in the first place. So which means it's going to take a long time for the execution to start. The second approach is to run this lambda expression with an interpreter. PowerShell is using the same interpreter as the link expression in .NET. So actually, we copy the code into PowerShell in version 3 with some PowerShell-specific changes and with some bug fixes to it. So what the interpreter does is that it's going to visit every expression node in the body of the lambda expression. And for every expression node, it's going to generate instructions for it. An instruction, okay, that's the, we're using the same interpreter. This is the one in .NET, and this is the one in PowerShell. It's been a long time, so I guess the code has been diverged a little bit. And an instruction is like every instruction in the interpreter has a run message. The run message contains some C# code that will be executed when the instruction gets to run. Instructions, work in a way as if it's on a single stack evaluator, which means, okay, for any run message within the instruction, it's able to read data or remove data from the stack, run some method, do some operation, push data back onto the stack, and do some other operations around the stack. So it's stack central. Everything is on the stack. Here is an example of one method. It's from the new array bound instruction. It's basically creating a new array based on the rank value you give it to it. So as you can see from here, the frame is the current frame on the stack. So it pops the current frame and casts it to int, which is actually the value for the rank of this array. Once you get that information, you create an array using this rank based on the type, and then push the array back to the stack. So that's an example of the instruction run method. Once interpreter generates all the instructions for this lambda expression, it will create a delegate, which essentially just points to an instance message within the interpreter. When this message gets invoked, which means when the generated delegate gets invoked, this message will create a stack and start to run those instructions one by one on the stack. So we have two approaches. One, for the second one, for the interpreter approach, the good thing about it is that it's really fast. It's faster to start. It's much faster than compiling a lambda expression into IL. So the user will get a faster startup execution. The drawback on that thing, on the second approach, is that the code is generated or the delegate is generated. As you can see, it's not as efficient as the IL. Especially the Jetter, .NET Jetter is able to do folder optimization on the IL generated from the first approach. So as we can see clearly, both approaches have its own, pros and cons. PowerShell tries to combine them together and take advantage of both. So by default, PowerShell will use the interpreter because it's fast to start. It's faster to start execution. It's people don't have to wait. It will feel like okay, instantly. And but for some hot script, for example, the script that runs many times, or for some hot code pass in the script, let's say we have a loop in a big script that runs many times as a loop. So for those kind of situation, we really want use a more efficient code. So the way PowerShell does it is that it defines a threshold. That okay, if the script is not large, it's relatively small, which means it contains less than, for example, 300 statements in the script, and the script has already been run by this interpreter for more than 32 times. If we reach that threshold, the PowerShell will compile the expression tree represented by the script in the background. And once the compile finished, it will switch the pointer to delegate and start use the IO delegate for subsequent runs. Similarly, for the loop in a large script, let's say the loop is not too large. The loop itself contains less than 300 statements in it, and the loop has been run in the interpreter for 32 times. PowerShell will compile the loop into IL and use that IL delegate to for subsequent execution. So in this way, PowerShell is able to get faster startup time, because it's using interpreter, so the startup time is going to be fast. And again, for a hot script or hot code pass, it's able to turn to the IL delegate for better performance. That's the interpreter. All right. Then now we have the delegate with a real executable code. It's either the IL code or the code the instance message pointing to instance message that's the delegate pointing to in the interpreter itself. So we have the delegate, and we're going to invoke the delegate, which is going to do the operations defined in the script. And besides that, the delegate itself will be saved in the script block, so that the next time you run the same script block, it don't need to be compiled again. You can just use the delegate and run it. In our example here, our simple script will run and generate some output. It will return back the folders and files within the C drive. And those results will be added to the output pipe, which will, like we taught before, trigger the do execute on the next command, which is our default. And our default, the do execute on our default will actually call into the process records on our default commandlet, which will take those input, this result object, and render it onto the console based on some predefined formatting. All right, so that's it. That's what happens, when you are typing a script and start to run a script on PowerShell console. And how much time do we have? Cool. So takeaways. This talk is mainly to answer a few, 4 questions. The first one: what are different types of commands executed in PowerShell? The answer to that is command processors. We have 3 different command processors. Each covers a different set of commands. And there are 4 key methods implemented by every command processor: do prepare, do begin, do execute, do complete. Second question: how are commands resolved? So given a command name, how does it resolve to the actual command? The answer to that is a command discovery component. PowerShell will do this scope chain search, and if that doesn't work, the module analysis will be triggered. So to analyze all the modules available in the module path, and do auto-loading if necessary, and return back the result. The third question: how are commands changed in the pipeline? The answer to that is PipelineProcessor. When you add a new command processor into a pipeline processor, this new command processor will be set as a downstream command of the previous command. So when the previous command reads out anything into the output pipe, the do execute method will be triggered on the downstream command. And that's how it's chained together, one by one. The last question: how is the script interpreted in PowerShell? Well, another way is how script actually runs in PowerShell. Answer to that is compiler and interpreter. Compiler is responsible to generate the real code represented as an expression based on the AST, the abstract syntax tree of the script. And then the interpreter is responsible to take that expression tree, generate a real delegate with the actual runnable executable code. And then you can run a delegate to start the operation of the script. So yeah, that's the takeaways. Now, any questions? Yeah?
Is there a way to force whether or not the interpreter gets used for the compilation to the IO?
Now there's no way to force that. Yeah, by default, PowerShell will use the interpreter, but it will turn to the IL if it has to, which means when you're running the code, if it reaches threshold, it will turn to IO. It's very similar, actually, to this tiered compilation concept introduced in .NET Core 2.1. So the tiered compilation 2.1 is like, okay, when the jetter starts to jet code from the IL, initially it's gonna generate less efficient code but faster. And then while the application starts to run, it will get more information about what code path is hot. And for those methods, we'll do further optimization, generate a better code for it, and replace the existing one. So in PowerShell, we actually kind of already use that concept way back in version 3.
When you talk about thresholds, can you set the threshold?
No, you can't. It's defined in PowerShell. Like, we tune it a little bit, so we don't think you have a better idea than us to define what threshold should be, right? Yep.
On the remote execution, for example, we have a server here in Singapore and the other one in Sydney.
Yeah.
And is there any minimum latency on the network? And what if the command is already pushed down and the return may be missing because of the network congestion?
It's not really related to this internal engine talk. In your case, then it's actually like the remoting is actually taken care of by the remoting commands, right? So it's happening within the command. It's not the engine that does the remoting. It's more like. Yeah.
And maybe in the future we can have an internal Docker remoting. I think the short answer is, if you use man and WinRM, it has protections in place so that it will try, if you get disconnected and stuff like that, it will retry to connect. If you're using SSH, then if that connection goes, your connection is gone.
Yeah.
But is there any minimum
So in this talk, we only touch some of the key components for this very simple script. Remoting is not part of this diagram. It's a whole big another diagram over here. All right, thank you very much.